Welcome to the QED-C Quantum Marketplace Quantum Computing Systems 3 event. We're very excited. We have a fantastic lineup, and we're just going to get into it here. So just a quick snapshot on format. I'll give a few updates on the quantum marketplace, some overview and trends in the space of quantum computing. A lot of exciting updates have been happening. We'll get into the lineup, and then we'll have a 35 minute roundtable panel discussion. So the quantum marketplace, what is it? It's a place to raise brand awareness. It facilitates collaboration, deals, and partnerships. That's been the feedback of many of the presenters. The quantum marketplace is comprised of two things. One is a directory on the QED-C homepage, which is publicly facing, which lists the various commercialization companies in quantum. You go there, you can get a description of what each one is doing. Also, if there's a pink icon next to their name, that means they've also presented in the quantum marketplace in the past, so you can see the video of their presentation there. Also, you can go to YouTube, just YouTube/quantum marketplace, and you can see all the recordings from our prior events. So for today, and this will all be recorded and posted on YouTube if you missed something or want to go back and rewatch. But we have IQM, we have Pascal, we have Alice and Bob, we have QCI, we have NVIDIA, and Microsoft. So some overviews and trends in the space. This is a pretty quick overview, but I pulled from April, McKinsey and Company. Of course, you can pull from Deloitte or BCG, Accenture, and the like about what's going on in this space. This is a overview of the entire quantum technology market. But what I want to highlight here, and what many of the other large consulting firms highlight, is potential for large economic impact and new business in the tune of trillions of dollars. You could argue it's smaller, you can argue it's bigger, but it's big. Data centers today, we are all pretty much aware of CPU technology, GPU technology, and I've listed some highlighted points or strengths of these technologies. But where is this going, right? Because these two technologies are not the best at everything, right? So in the future, data centers, now this could be on-prem, like on your premise, or this could be in say a multi-tenant data center or some other data center in the cloud. And where we're looking at, well, what's the future going to look like? Well, it's probably going to have CPUs, GPUs, and then also QPUs and NPUs. Well, what are those? Those are quantum processing units and neural processing units. And I've highlighted the strengths of each of these, somewhat debatable, but these are, how some of the people here will be looking at least QPUs is what we're covering mostly today. Also, there's a lot of conversation in the marketplace about AI, be it generative AI, be it AGI, be it whatever it is, and quantum computing, and how do these two interrelate with each other. And quantum computing is all about harnessing entanglement, right? And what can you do with that? Well, you can, for an example, you could look at Shor's algorithm or quantum chemistry. Because there's underlying structure and what appears to be random, entanglement helps us get there. So that's something to think about. And then AI, how does that help quantum computing, or does quantum computing help AI? The preliminary theory here is that AI can be creative and can be harnessed to better run quantum computing because it's more creative, whereas quantum computing is more about entanglement. Okay, lineup. So Miko, we have Miko, who's the CEO at IQM. He'll be going first. We have Michael Warren from Pascal, who's the VP of Sales of the United States. We have Juliet from Alice and Bob, who is recently appointed U.S. General Manager there. We have Andre, Head of Product at QCI. We have Nick, who's a marketing lead in quantum computing at NVIDIA. And we have Matt at Microsoft, who's the Principal Technical Program Manager. And with that, Miko, let's have you share your slides.
So thanks, Mark. Thanks for the opportunity to have this brief talk here in this webinar. So I'm going to briefly talk about IQM and what we do. So IQM is a European company. We are kind of Finnish-German company. And what we do is we do full stack quantum computers. We build them and we deliver them. We have our own chips, what goes inside the computer, and then we build everything together from various components. We put all the software inside and we deliver to customers. We are about 300 people today. We are very heavy on R&D. There's a lot of investment in our company. We see ourselves as the market leader in Europe, and our goal is to be number one also worldwide. We have sold these really big systems already in Germany and Finland. That kind of shows we are able to build and deliver. And we have today what we see is this most comprehensive product portfolio in the market for different price points and budgets. And we also heavy on R&D, like I mentioned. Our approach is superconducting qubits, and we see ourselves as the technology leader, definitely in Europe. We have our own fab. Nobody else has such a capacity in Europe at the moment. And we have some proprietary technology, especially on the error correction side. Let me see if the slide changes. Yes, here's our product portfolio. So we do both on premises and cloud. And on premises, you see on the left-hand side and cloud on the right-hand side. On premises, like I mentioned, we have different price points. And we have the first product, which is full stack, complete quantum computer with all the software, all the hardware at less than 1 million. We call it IQM Spark. It's a complete 5-qubit system. And we have seen a tremendous demand in the market, not just in Europe, but worldwide. We're going to have an announcement soon, both in North America and Asia for this Spark setup. Then we have this kind of bigger system we call IQM Radiance. We have today 3 configurations. One is 20-qubit configuration. Then there's a 50 or 54-qubit configuration. And the biggest one is a 150-qubit configuration today. And the biggest one is able, with the latest error correction technologies, actually already demonstrate what we see in the near future. We are getting to the quantum advances direction. The biggest system is still under R&D, and we are expecting to deliver the first customers next year. But the 20 and 54-qubit systems are something we can deliver in pretty short times. Then we have our cloud offering and service offering on the right-hand side. We launched just this spring our IQM Resonance Cloud platform, which has been getting very good reviews in the market. Others also provide their cloud platforms, but as we are kind of late to the cloud, we have really thought out how to build this cloud. We have a comprehensive algorithm library coming in there. We have a system which actually gives you easy access. There's almost no lines when we use our system on the cloud. And there's 2 processors currently available. One is a 20-qubit processor, then there's a 6-qubit processor, and in a few weeks, we will have a 50-qubit system also available on the cloud. Then we have our service offering, and part of it is something we call IQM Academy. So we have a kind of learning platform online, free of charge, accessible to anybody. And with our customers, we have even more content available when they buy system from us. On top of that, we typically work with our customers on different use cases. We have our own algorithm team inside IQM. So if there's any industry application, we are always willing to help and understand use cases really matter. And we're going to invest more in the software side, in the algorithm side in the future. There's 2 quick slides about our competencies on the hardware and software side. This is a short presentation. I don't go into the details here, but just give you a glimpse. We have key IP in important parts of the low level of the technology stack here about the QPU. So we are using something called tunable couplers. We have our own IP on error correction and error mitigation technologies, which are very key for the future use cases. Also on the software side, this is something we are really investing, and we think the industry has kind of underinvested in the past. Because we built the full stack, we really have been looking at the whole software stack and how to, for example, get rid of this Python code, which is everywhere in this industry. I'm coming from a software background myself and really see that we have to work on the software stack more in the future. We are building a single stack for both on premises and cloud. We have for users free choice of tools. You are not tied to just one set of tools like some other vendors are working on today. and we want to integrate the systems very, very tightly to the customer systems, for example, HPC centers and supercomputers. This is in brief what IQM does and what are our strengths. If you want to get in touch for Europe and APAC, I'm the first right contact point in North America. Our head of US sales and is Robert Conan. He can help you with whatever inquiries you will have.
Thank you, Mikko. Michael,
Thanks.
You're up.
Thank you, Mark. Appreciate the opportunity to speak to this group today. On behalf of Pascal, Michael Warren, Vice President of U.S. Sales and for Canada as well. And we appreciate the opportunity to tell you a little bit about Pascal and our neutral atom technology. To start out with a vision, our ambition is to break through the limits of computing by leading the delivery of state-of-the-art computing. Very scientific in nature, but really our goal is to take that vision and drive it from the scientific world, from global innovation and into the enterprise. So what we deliver is hardware and solutions that drive your business and deliver ROI. We don't want to concentrate on just scientific experiments, but we want to deliver ROI for our customers and partners. We were founded in 2019. We're based in Paris. Our vision and mission is very pragmatic, very customer-centric. Our co-founders believe that neutral atom technology can deliver value to the market in the near term or today. And this vision is really driven by a unique mix of science and engineering. In short, we know how to take quantum technology out of the lab, make it reliable and transportable to deliver results to your customers. And this customer-centric approach to our enterprise partners and customers has enabled us to grow from the 3 founders you see on the screen here to over 200 employees with a global footprint. From a financial perspective, we're VC funded. We've raised over 125 million euros from top-tier VCs, which you can see on the screen there. And that's really allowed us to fund our business. And I'm going to concentrate on 2 areas on this slide. The first is R&D. Our goal is to reach 1,000 trapped atoms in the next 2 years. And the other main point of this slide really is using the money to fuel our international expansion, especially in the US. Right now, we are a global company with a presence and customers in 8 countries around the world. Notably, we're delivering on-premise QPUs to Wippich and Gen-C in Europe, and we're currently working with customers in the United States and Canada. We have 2 manufacturing facilities. The first is in France, and the other, which is coming online right now, is in Sherbrooke, Quebec, where we have a machine. And we also have QPU assembly in the United States. Our goals for 2025 and 2026 is to launch a US-based manufacturing facility. And to that end, we're talking with a number of US states right now to form partnerships and collaborations to bring the power of neutral atom to the US ecosystem. As you can imagine, all of this has resulted in tremendous traction for Pascal. A few of the most notable ones, we have a relationship with IBM where we're defining the future of quantum and HPC. We have a collaboration to optimize maritime and logistics operations with CMA, CGM, a number of high-profile customer events with BCG, J&J, BMW, IDC, with the Minister of Digital Affairs in France. And keeping with that vision statement and driving quantum computing down to the enterprise, we delivered a 100-qubit machine, QPU machine, I should say, to Gen-C in Europe. It's marketing our first QPU delivery to a third party. What's appealing to this group and why we've been successful is the strength of our roadmap. Right now, we have available a 200-qubit Orion Alpha device. That's already run many use cases and implementations for our customers, including molecular chemistry, optimization of 5G networks, and quantum material investigation. Next on the roadmap is a 1,000-qubit Orion Beta machine and Orion Gamma device that will be available in the coming years for on-prem delivery. If you take a look at the roadmap going out to 2026, we have our 10,000-qubit device Vela, Pegasus, and Centaurus, the latter of which is our fault-tolerant quantum QPU. And we also have a cluster of NVIDIA GPUs to run our neural atom emulator in the background there. On top of that roadmap, we offer a full stack of solutions to support our customers, from access to platforms, solutions, and libraries, and also a full complement of training and tech support and maintenance for general QPU usage. We're often asked one question, and what are the benefits of neutral atom technology in the quantum space? And the quick answer is, from a data center perspective, our neutral atom devices are compatible with standard data center environments, using industrial off-the-shelf parts, relatively low energy consumption. We feel this reduces the barriers to entry for many data centers to bring QPUs into their HPC stack. And again, that's something we're working with IBM on. In wrapping up, our business model is quite simple. We have three offerings. The first two related to accessing our QPUs, which can either be on-prem in your data center, or you can access via the cloud via a third-party data center, or from your quantum scientists working in-house. And then we also offer software and applications, including platforms, solutions, and libraries, all of which we can explore via customer proof of concept to assist with use case development. So with that, thanks for your time today. Please don't hesitate to reach out if you'd like a deeper dive on Pascal and our neutral atom technology. And with that, back to you, Mark.
Okay, great. Thank you, Michael. Juliette, get your slides up.
Well, hi, everyone. Thank you very much, Mark, for having me today. I'm Juliette Perronnet, the US General Manager of Alice & Bob. We are a hardware startup based out of France, with headquarters in Paris and a US branch in Boston. We are leveraging CAD-qubit technology to build quantum computers, and we believe that this approach is going to allow us to build the first universal quantum computer. We were founded in 2020 with more than 100 employees to date, and trusted by global key partners. Just want to highlight the work with Microsoft quickly. We have been able to implement within their quantum research estimation tool our CAD qubits. So if you're curious in benchmarking how many qubits you need to run your algorithm, you can do it with our technology on their tool. In the past few years, we've seen that quantum players adopted different approaches to scale their technology. Some of them are increasing the number of qubits to reach the NISQ regime with physical qubits, and then thinking about implementing error correction. Others are thinking about error correction from the get-go and thinking about reaching the FTQC regime right away. We think that this approach is the right way to go for many reasons. The first one is that when you're thinking about algorithm developments, you're not going to implement the same algorithm on NISQ machine that you're going to do it on FTQC machines. So all the work that you've been doing might not be directly useful. Also, when it comes to the compilation layer, there's a lot of work that needs to be done to allow logical qubit to be implemented. And as a reminder, at the FTQC level, this is where there's a proven quantum advantage. That's why at Alice & Bob, we are only focusing on this regime to provide advantage to our customers. In terms of what we achieved so far, we are the first provider to have developed CAD qubits and released them on the cloud, on Google Cloud. They're currently available. We own all the IP behind this technology. We are pioneers in error correction. You need 200 times fewer qubits for impact with our technologies than others, and we're compatible with error correction, the latest error correction schemes, which allow us to reach the fault tolerance regime faster than others. In terms of qubit quality, you have those two main errors that prevent you to reach the logical level, and we have a worldwide record in terms of bit flip time of more than 100 seconds, and we are now focusing on limiting the phase flip errors. To be more concrete, what does it mean? If you're comparing the error rates needed to have the equivalent of a 49 physical qubit machine with Google, you will only need one CAD qubit. In order to implement your algorithm, which is when we reach a commercial advantage. You will need 20 million physical qubits with Google machines and only 100,000 CAD qubits. So right now, when all the players are thinking about reaching this commercial advantage, scaling their machines to reach the FTQC level, we have tremendous advantage, and doing so as the engineering overhead is way lower than others due to our advantages of reducing the number of physical qubits to a logical qubit. If you want to work with us, we work extensively with industrial partners and the academia. We have a consulting offer called the Box, where we are meeting our partners where they are. We can help you to understand quantum computing and its impact on your business, to build your strategy and identify value of quantum computing for you, and get ready to leverage the CAD qubit technology as logical qubits are coming. We have identified more than 120 use cases across industry. We have world-class quantum experts and consultants that we hire directly from McKinsey, and trusted global partners and customers. So if you want to learn more about CAD qubits and why this technology is providing tremendous advantage over others, feel free to reach out. We are also building many academic and technological partnerships to accelerate our roadmap and also help the community. And if you want to leverage CAD qubits inside your quantum roadmap, feel free to reach out as well. Thank you very much.
Great, thanks, Juliette. Andre.
Thank you, Mark. Thank you for the opportunity to speak. My name is Andre Petrenko, Head of Product at Quantum Circuits Incorporated. I'd like to tell you a little bit more today about our company and about our unique quantum computing solutions that we're developing and that we think are really exciting going forward based on dual rail cavity qubits. I'll start off with a brief profile of QCI. We were founded in 2017 as a spin-out from the quantum computing labs at Yale University. We have a pioneering team of founders, including Rob Sholkoff, and we're venture-backed, including by VCs, including Sequoia Capital, Canaan Partners, and other really high-profile VCs in the industry. We build really revolutionary quantum computing systems, unique systems that are based on breakthrough qubit technology that's called the dual rail cavity qubit. And it's not just the qubits that we're developing, but full stack quantum computing systems capable of universal quantum computation. And I'll tell you a little bit more about that cavity technology on the next slide. So the dual rail cavity qubit is comprised of two superconducting cavities, and the quantum bit of information is encoded in a microwave frequency photon. The photon is in cavity 1, that's our logical 0. If it's in cavity 2, that's our logical 1. It could be in a superposition of the two. And we can have multiple dual rail qubits coupled together to perform multi-qubit gates. We also have measurement devices connected to these cavities to measure the state of the photon and also detect whether the photon has disappeared. And that's the primary source of error in these systems. And that's a really unique differentiating quality of these dual rail qubits that really makes them unique in the industry. The fact that this photon can spontaneously decay, and that's really the built-in error detection system that we have at the qubit level. And that's really a novel tool for us at the algorithmic level that enables us to develop new algorithms, and also is a key stepping stone for quantum error correction going forward. And this is not just at the dual rail qubit level. We are building up full quantum computing systems where error detection is a key component that bridges the gap between physical and logical qubits. And so this is a cornerstone of our strategy, where we correct first and then scale by perfecting the hardware and the software, increasing the size, having a grasp of the performance of the system and the system expectations along the way. And so we look forward to move beyond the conventional NISQ approach out of the gate and addressing the novel challenges with the error detection approach in dual rail qubits and the quantum computing systems that they comprise. And in this way, we really lay the foundation through partial error correction, going into the fault-tolerant era into quantum advantage on an expedited timeline that we believe is more efficient, and that we think really sets us apart from all the other approaches that are being pursued in the industry today. In addition to this kind of hardware approach, we're also introducing a number of unique programming features into our toolbox. And the primary, one among them, we call error awareness. And that is, again, a new feature in our toolbox that builds upon error detection. And with error awareness, we allow users to integrate real-time control flow and advanced embedded classical compute options. And what this really means is that classical outcomes can really dictate the flow of quantum subroutines, presenting the tightest possible coupling for classical and quantum in hybrid applications. And this really offers a whole new class of possible algorithm development for users. And we think it's a really exciting feature that users are going to be, able to leverage today. We offer that in our simulation platforms and in our QPUs going forward. We offer, as I said, full stack quantum computing capability. And that starts with quantum as a service through our cloud platform. We offer an SDK and a simulator today to select customers. And going forward, we'll be offering a compiler and a quantum processor to accompany these tools and round out the full stack. We also offer an alpha program today where you can partner with Quantum Circuits and really access these cutting edge quantum systems and simulators and really be among the first to use them and explore our feature-rich API with the error detection, the error awareness, and the real-time control flow and embedded classical compute. If you're interested, we'd love to work with you. Please reach out to us, partner@quantumcircuits.com, and explore with us. Thank you.
Great, thanks, Andre. Nick.
Thanks so much. So my name's Nick Harrigan. When I tell people I work at NVIDIA and on quantum computing, inevitably the first question I get asked is whether NVIDIA is building a QPU, whether we're building qubits. And I can start off, preempt that question. NVIDIA is not building a QPU, but NVIDIA is trying to build the systems that will be able to make qubits useful. So the systems we will need for useful quantum computing. So we are trying to build accelerated quantum supercomputers. And I will explain, hopefully, by the end of this, what I mean by that. So it's not just a new term to introduce. And so it makes sense that a company like NVIDIA would be working on a problem as important as quantum computing, arguably one of the most important computing problems we have today. But it also makes even more sense as to why we're so pivotal in this kind of field when you look at our history. So NVIDIA has a large history of enabling computing revolutions. And as we see it, those revolutions all kind of build on each other. And so to us, like quantum computing is kind of the next logical step in accelerating things with new modes of computing, and one that we think, a revolution we think is going to build on our knowledge in the previous ones. And so that's why we partner extremely broadly across the quantum ecosystem to try and build these accelerated quantum supercomputers. And so if there's one thing we're definitely in the market for, it is more partners. So if you think that we can partner with you with any of the stuff I'm going to talk about, please do reach out. We're very keen for that. This is how we're going to make this all possible. And I wanted to spend the rest of the time just quite quickly going through what I mean by everything I just introduced. So how are we trying to build an accelerated quantum supercomputer, and what does that mean? So I think it's kind of universally understood now by the community that to get to useful quantum computing, there are a few challenges. I've listed some here. I'm not going to go into any details about them specifically, but we kind of posit that all of these challenges need very powerful tools for both the development of the computers we want and for the operation of them. And that the tools that are sort of readily available to most of the researchers and developers today are not really going to cut it. So, for example, current QPUs are fantastic, and we're definitely, working on some really exciting systems. But of course, we're not quite there yet with useful quantum computing. And moreover, what we'd emphasize is that we think that those tools alone are not going to be enough to take us to the next level. So we also need really powerful simulators. And the simulators you would have available to you with just CPUs or even single GPUs are also not really powerful enough to solve the kinds of problems that simulation is going to focus on for the future of large-scale quantum computers. So things like tensor network simulations, when we start looking at large systems for error correction, dynamical simulations of hardware for like reducing the noise in qubits and understanding how to get to the thresholds we need for error correction, and lots of other things as well that might actually be relevant for introducing techniques like AI into how we develop quantum computing. And so what we think is that GPU supercomputing is going to be the key for enabling large-scale quantum computing, and for a number of ways. So as I just mentioned, GPU accelerated simulations will be key. We're very active in AI for quantum computing, something that Mark mentioned at the start of the session. So finding out how AI techniques are going to be helpful, not just in simulation and algorithm development, but also in actually running a quantum computer. So things like decoding, AI decoders and calibration techniques. And then also the actual supercomputing infrastructure you need to put a QPU into to run it. So we are doing a lot of work to try and understand how like GPU acceleration and AI techniques are going to be useful for those operational tasks. So again, decoding, calibration, measurement readout, those kinds of things. And so that's what we're doing. So we're working with a lot of centers of excellence, high performance computing centers across the world. I've just called out two here, IIST in Japan and Gefion in Denmark. And we're enabling them, we're giving them the tools, the GPU supercomputers, so that researchers can build, well, the whole quantum research ecosystems are building around these devices, because they let people study the kinds of things they need to get to the next level. And we're also working with partners, some of which people have already talked about this, taking QPUs into supercomputing centers and experimenting with actually connecting those devices together to allow hybrid algorithms, to allow hybrid quantum classical computing. And we have a product line that kind of supports this. So overarching in our product line is QED-C, which is our accelerated quantum supercomputing platform. And this is a software product that is built very much from the ground up for hybrid quantum classical computing. And so this is something that you can plug in as a backend, a simulator. So we have QQuantum, which is like the fastest GPU accelerated simulator there is for state vector and tensor network simulations, but also it's completely hardware QPU agnostic. So you can plug in one of any of a large number of QPU backends to this. And moreover, when you're thinking about the reality of actually performing quantum algorithms, where you need access to both GPUs, QPUs, and CPUs, we also have QED-X as a backend, which has got the world's fastest implementations of many of the algorithms and tools you will need for the classical side of those hybrid algorithms. And so that's kind of where I wanted to wrap up. I'm obviously happy to talk much more about this in the discussion, but I've had some links there for you to find out more about what we're doing. And thank you very much for your time.
Thank you, Tim. Matt.
Thanks. Hey, Mark, thanks for the opportunity today. Just sitting here and listening to all the innovation encapsulated in such a short period of time for presenters today, it's just super exciting to see the collective progress being made across the quantum today. I'm happy to be a small part of it, working at Microsoft on the Azure Quantum team. I spend most of my days driving our logical qubit efforts forward, which I'm going to share a bit more about today. And I'm hopeful just in the few minutes I have is to share with you some of the key efforts we have that all ladder up to a mission to accelerate scientific discovery. So I know that just sounds like some interesting words, but really everything we're doing on a day-to-day basis is directly accruing to this big goal we have. And we think of our work being carved into three separate pillars, if you will, but all, of course, interrelated. The first and foremost, quantum computing. We'll talk a bit about that today. We also are very keen on evolving how applications will take advantage of quantum computers in the not so distant future, and particularly focused on chemistry, material science, and drug discovery for that. We'll talk about some products we have to help that along. And lastly, quantum networking, right? So we have some investments aimed at how to build future interconnects between quantum supercomputers and such, so that all this can come to market in a viable way, targeting commercial advantage in the future. So we try to take a really simplistic view of the quantum computing domain, right? Carving it into three levels. So level one, foundational. This is what everyone's really familiar with today. Physical qubits. Yes, you can prove out quantum advantage with some physical qubits, but it's on very contrived problems. I think everything, a common thread I've heard from everybody today is this push towards level 2 or resilient or reliable quantum computing, right? And this is the advent of logical qubits, right? Where you really start to scratch at scientific advantage for certain problems around 100 logical qubits, and lots of work going on in this space. And we'll go into some more depth in a second on that from our perspective. And then finally, everyone's driving toward this idea of scale, right? Where you can realize a true quantum supercomputer, get after a commercial advantage. And that's something that we see interchangeable with fault-tolerant quantum computing or utility computing. So very much aligned with everybody else today in that regard. So looking specifically about this transition from level 1 to level 2, we're really, really proud of some recent co-innovation we've done with a longtime partner, Quantinuum. They're an ion trap quantum endpoint, known for their very high fidelity ion trap qubits. So recently we were really excited about working together, combining Microsoft's qubit virtualization system on top of those high fidelity ion trap qubits to build what we believe to be the most reliable logical qubits on record today. And we demonstrated and published the ability to show up to 800x improvement in error rate when comparing logical to physical for the same circuit operations, right? So definitely stepping into that realm of reliability with those results. And for those that are deeper on the error correction side, we were also to demonstrate multiple successful rounds of syndrome extraction, right, without disrupting that circuit. So that is truly a foundational element on that path to fault-tolerant quantum computing. So we're really excited about that result. And then what are we going to do with this progress, right? So I mentioned chemistry and material science at the start. Our CEO, Satya, is really good at coming up with very concise statements that represent big missions for the company. And I love this one. Our goal is to compress the next 250 years of chemistry into the next 25, right? Harnessing all these great advancements. So how do we plan to do that? We have a really cool product called Azure Quantum Elements. The idea, a lot of depth here, we'll just gloss over it for now, but the idea is combining high performance compute to the scale that affords, the speed through AI, and the accuracy of quantum endpoints, right? So customers can bring on their computational chemistry workflows to this platform today, and then as that quantum endpoint continues to advance, they can use that to increase the accuracy more and more for chemistry simulations and whatnot to accelerate scientific discovery. So if you're keen to learn more about Azure Quantum Elements, hit that QR code. I'll copy the link over in chat as we go today. And also, if you're interested in learning what's under the hood for that recent reliable quantum computing demonstration with our partner Quantinuum, there's some more information as that provided there as well. So thank you.
Thanks, Matt. Great. All right. So I just want to thank everybody. That was fantastic. And just going to jump right into the panel discussion here. I'm going to go to Juliet first, since she's the one who suggested this. I took a little bit of a spin on this, but essentially there's been a shift in the market. Some even government funders and whatnot are starting to shift the narrative. We've been in a NISQ era for quite a while, noisy intermediate scale quantum, with a shift to fault-tolerant quantum computing, and even Matt touched on it in his presentation. Utility scale, right? So, Juliet, why don't you give your perspective on this, and how is your organization approaching this?
Yeah, thank you, Mark, for this. So, as I was mentioning during the presentation, this is the entire focus of Alice & Bob. We are not trying to build any type of a NISQ machine, and the first reason is that it is because FTQC has been proven to be where there is commercial value. So we want to make sure that that's where we focus our attention and our resources. And I've been working in the industry for almost 5 years now, interacting with customers, potential partners, and so on. And I remember when I first started, the first question were, why should I focus on quantum computing right now? And then the question evolved to, okay, I'd like to run something on a hardware today. What can it be, and can it provide some sort of advantage? And now that those customers have done their testing and done initial work on these devices, and some of them didn't find some of the value that they were potentially expecting here, they are gearing their attention toward FTQC. And this is what we are promising at Alice and Bob. The type of algorithm development that we're doing is fully focusing on FTQC development, even if it's still theoretical because we don't have the hardware. This is where we think we can gain an advantage with our customers. Now, when it comes to governmental agencies, there's been tremendous funding both in Europe, in Asia, in North America for developments of quantum computing, and that's great. And we've had tremendous support from government. And recently, especially in North America, we've seen that agencies like DARPA or ARPA-E has changed their focus toward FTQC development solely. And this is a great sign for us industry player that FTQC is the regime we all need to focus on, even if, of course, education is key and all the players that are doing NISC work is really valuable to help the industry getting there. We are seeing that things are changing, and Alice and Bob has been taking this initiative and of solely focusing on FTQC from the get-go.
Okay, great. Thank you. Andre, any thoughts on this?
Yeah, I think Juliet makes a number of good points there where FTQC is definitely, the long-term goal where we want to get to, where the field wants to get to. I think in the near term, though, over the next couple of years, there are a couple of, features, software features, lower level hardware features on the quantum hardware that might enable some interesting, breakthrough algorithms that might bridge that gap between where we are today and where FTQC can provide that breakthrough value. Specifically, the real-time control flow embedded classical compute and the error detection that I was mentioning earlier, that could lead to either partial error correction or really algorithms that we haven't even thought of today. So we're really excited about thinking, through those opportunities. And so hopefully, looking to work with others on those as well.
Yeah, great. Michael.
Hi, excellent points from everyone. What I see happening in the corporate marketplace, as we march towards fault-tolerant computing, is a need for corporations to understand what sort of intractable use cases they're pursuing right now and how that can provide ROI. And I think it's a very step-by-step, approach to that, where identifying an intractable use case, figuring out how many qubits there are, and trying to solve it. At the same time, you need infrastructure that can fit into your existing data center footprint, whether that's going to be in-house or a third party, or if you're accessing during the cloud to get a start on that. So creating a lower barrier of entry so companies can start to do that other than looking at simulators. I think that is the way to go, and something we've been hearing from our customers in the US and Canada, as well as the EU and Asia.
Yeah, great. Thanks. Miko.
Yeah, thanks, and good point from the other people here. So our approach actually is a little bit different, what we heard here. So at IQM, we believe that actually in NISC era, we should be on the market already. And it's actually not as a black and white kind of transition from the NISC era to the fault-tolerant quantum computers. Currently, we are working with our 20 and 50 qubit chips already with error correction. We are tuning things like the qubit design itself. We heard that Alice and Bob has their own qubit design. We are using the most popular superconducting qubit design called Transmon, but Transmon from 2020 is different than Transmon at 2024. We are actually implementing some error mitigation technologies inside the qubit design. We are working on the topology of the chip, what it looks like. And all these little improvements are getting us closer and closer to the fault-tolerant quantum computing. So it's going to happen in kind of small steps at various instances. And our 150 qubit chip, what we're going to release next year, with different error mitigation, error reduction, and also error correction algorithm technologies, what we are going to implement there together with our partners. I think we are going to get very close of being able to run some of these algorithms which are believed to be kind of very distant in the future, or just some time ago people were thinking about this is not today but in the distant future. So our approach has been on the market, working together with all the customers and partners with the current technology. We believe this is the quickest way, the practically quickest way to fault-tolerant quantum computing. So it's not going to be, in the future, one day the sun rises up and we are there, but it's a gradual path there, and we want to really be on this path.
Yeah. Thanks, Mikko. Matt, I mean, you guys are doing topological, you're partnering. How are you looking at this?
First off, I'm getting used to going last year. My family name ends in Z, so it's just.
You're going to go first on some of the
something
other
I'm very used to. So
right.
a couple. We have a lot of thoughts here. I think general agreement with a lot of the comments that are already made. Especially this idea of this being not a square wave transition, right? This is a transition, as I tried to show on that one slide where we level the 3 levels of quantum computing, if you will.
Right.
So I think there's this transition towards reliable quantum computing. This is really important, right? This isn't just this throwaway step towards fault-tolerant quantum computing. There's tons of innovation going on here, and anybody that's trying to prepare for fault-tolerant quantum computing can do an immense amount with these capabilities as they get better and better. So that's one thing, right? This sort of nice transition to FTQC. And then, as you mentioned, Microsoft, we have a couple parallel paths here. I mentioned this in the chat. We are still very bullish on our first-party efforts around topological quantum computing.
Right.
We've had some great progress recently in that, and I shared a link to a nice summary of that. And then we're working directly on co-innovation with a handful of partners, right? With that recent result with Quantinuum, being able to pull 4 logical qubits out of only 30 physical qubits, right? That's pretty impressive and really pushing on that transition towards fault tolerance.
Yeah, great. Thank you. Nick, you get to clean up on this one. Since you guys aren't doing QPUs, how are you looking at this?
Yes, this is a great question. Everyone's kind of said, I think, a lot of the most important points on this. But the thing from us, I think we say, is that we're partnering with everyone. So we're keen to enable people in all the kinds of approaches they're considering. Though we are very interested, of course, in fault tolerance. It is becoming increasingly clear that this is going to be the path, I think, to commercially useful quantum computer. And I would emphasize what Michael said, which is that a lot of the challenges you face to do that are infrastructural challenges, and you really need to think about fitting this thing into a data center and how those things are going to work together. And so we're kind of focused on that. We do think this is the way to go. And one of the ways we're approaching this as well is with AI tools. So we had some work recently on a generative quantum eigensolver, which was using AI tools to try and better understand how applications can do more with less. So that's kind of one interesting tack. And also thinking about those challenges like decoding, how we can actually get, QPUs next to the hardware so people can start experimenting and start doing the kind of work they need to approach those quantum error correcting related challenges. So we work with quantum machines. We have this reference architecture called DGX Quantum, which is basically a way that you can put an IO system into our kind of DGX SuperPod GPU accelerated supercomputer system, and then connect a QPU directly to it. And quantum machines have recently announced an Israeli quantum computing center where they're using this reference architecture to put their OPX next to our DGX SuperPod hardware, so that they actually are going to bring in now. So Orca is one example of QPU companies that are going to be coming in and working with them to put QPUs next to that hardware so they can start to solve these challenges. So our approach to it is to help people solve these challenges and to make fault tolerance a reality.
Yeah, great. Thank you. I'm going to go to the next question here. I'm going to start with you, Nick, since you suggested it. What is the future of simulation in quantum computing? Is it going to die on the vine, or is it going to be helpful as a tool? Please expand on this.
Who would have guessed that someone from NVIDIA would suggest this as a question? Yeah, absolutely. So the point I want to make about this, I guess, why I'd like to answer this question is I think there's a general kind of view, or there can be a view, that simulation in quantum computing is a kind of anachronistic tool, is something that was useful in the NISQ era, when systems were small enough for us to simulate, to do circuit simulations.
Let me stop you there. I'm going to ask you to define what this is, because I think there's people in the audience who probably don't necessarily know exactly what we're talking about now that we're talking about it. Yeah,
it's important as well, because the word quantum simulation can mean two very different things, right? In some sense as well. So I'm talking about trying to simulate with a normal computer how a quantum computer will act when you don't necessarily have one, or have what available or in existence yet. So it's like the idea that you might be able to help yourself develop applications or investigate how the machine might work before you actually have it by simulating it on a normal computer. Now, of course, there comes a point where you can't do that. If that didn't happen, you wouldn't need a quantum computer ever. You'd just simulate the thing on a normal computer. You'd never have to build it. But it is possible to simulate it up to a certain level. And that can really help people in developing hardware and software applications and algorithms for the quantum computer. And so my kind of point was that, people think in the NISC era, this was maybe a useful tool because you were interested in simulating smaller, not so difficult systems. But in fact, the simulation is going to remain a very important tool as we go forwards. There are techniques to simulate larger systems like tensor networks that work for certain kinds of applications. But moreover, I think we're going to see a real increase in how people use simulation to actually study hardware, so dynamical simulations. And I know a lot of companies are building out these really sophisticated tool chains that let them understand how noise propagates up through their system, all the way from like the level of their physical hardware through to the actual logical operations they want to perform. And as we start thinking about doing error correction and fault tolerance, that's going to be an increasingly important tool. And so I think that GPU supercomputing as a way of accelerating these simulations is kind of the future of taking us into that fault tolerant era.
Great. Thanks for that, Nick. Matt Zander, you're not going last, so I really want you to jump in on this one. I'm sure you have an opinion here.
Yeah, it's kind of a boring opinion, because I think it's identically what Nicholas just described. So, today a lot of emulation hits a wall around dozens of qubits, right? It's just it becomes really hard to model some of these more complex algorithms and approaches. So having this continued advancement in simulation is just critically important, right? As we try to move our way through these transitory lasers to fault tolerant quantum computing. So I think it's wonderful work that's going on and needs to continue and accelerate, in my opinion.
Yeah, great. Andre, any comments on this?
Yeah. Well, I think, a lot of this was covered from the high level, like how it's going to affect, users in terms of developing algorithms and, prototyping them, which is always going to be, simulation is always going to be an effective tool there. It's going to cut down on costs, so you're not developing algorithms on expensive QPUs. I'm going to put my education hat on right now, coming from graduate school, where when you're designing a qubit or a couple of qubits, you need a variety of simulation tools there. And I think for any students out there listening, whether now or who are going to be watching on YouTube, they're going to have to understand that things like QTIP or HFSS or any modeling tools out there are always going to be super helpful, super useful in designing qubits and understanding their dynamics before they even start putting hardware together and assembling it, because that's really going to dictate how that quantum computer comes together. So
yeah, great. Thank you. Miko.
Yeah, we are very happy that people use quantum computers in whatever way they want. Emulators are the great kind of first entry point to quantum computing, so it's obviously great. If there's a user, then there's demand. And as somebody who's on the market today, we are happy to sell you can call them noisy computers, to all the users. So we see actually this works in parallel. So while those who have simulators or emulators today, they may keep on continuing to use them for certain workflows and use case and experiments, they can also acquire then a noisy computer on the side and keep on expanding their kind of capabilities from there. So we see this as a kind of natural entry point to quantum, and we believe there will be need for emulators and simulators also in the future.
Yeah, great. Thank you. Juliet.
Yeah, definitely agree with what was said. And when we're thinking about studying how an algorithm is going to scale, like this is very key to test it on emulators. And those are great tools to both R&D and also educational tools. So we need to continue to have initiatives to build better simulators and to make sure they're available.
Yeah, great. Thank you. Michael.
Yeah, I think simulators are going to be a key component in the toolkit, looking at quantum and looking at intractable use cases. I think over time, what will happen is as the qubits get better, people will start using or running those types of problems on quantum computers. So you may see a tipping point, if you will, in the future. But I don't think it's ever going to go away. It's a great first crack at these problems. And like I said, it'll be in everybody's toolkit for the foreseeable future.
Yeah, great. Thank you. I'm going to skip that one. So it can be complicated for end customers to figure out how to assess various quantum computing solutions today. And so, so how important are hardware systems and application benchmarks in this assessment? I'm going to start with Andre. His colleague, Tom Levinsky, is here as well, and this is like his lifeblood, I think. Somewhat. So Andre, I'm going to have you channel Tom here a little bit and sort of set the stage.
Yeah, so do you want me to go first or Tom?
Yeah, no, I want you to go first.
Jam.
Yeah, I want you to go first. You guys have
Okay.
done a tremendous, I'm not saying the others on this call, I mean, others on this event haven't, but you
Sure.
guys have done a massive amount of work in this.
Yeah, no, I mean, look, from my perspective, I think benchmarks are absolutely crucial in this field, and the fact that we've made so much progress on coming together and getting from an application standpoint a set of benchmarks going in this field that go beyond single qubit level like T1s and T2s and so forth is just fantastic. I think it's difficult for customers who aren't, in the know in this field, who haven't come from this background to get a sense of, what do I buy? There are so many hardware platforms out there, so many different modalities, and just having like one plot to look at, having, one image to look at, having one benchmark to look at that tells them this is the performance of the system is really important. I would caution though that while that is a very helpful metric, this application focused approach, I think in the end there are going to be multiple winners in the field. And there are going to be, certain hardware platforms that might be more appropriate to solving this class of problems versus that class of problems. And so I think, it's not just qubit performance. There's also system throughput that's really important. And we have to continue iterating and developing benchmarks that classify that. So I think this is still an ongoing process. I think customers still need to, be educated and continue being educated on that. I think things like classical compute and real-time compute is, still needs to be incorporated. So we're at a really good spot right now. I think there's a lot more work to do. So I'm just excited to see what's going to come next.
Yeah, great. Matt, what's your view on this, or what's Microsoft's view on this?
I agree with everything Andre just said. I think the progress made already is really impressive, right? And I think I'll only add that we need to think about benchmarking as it relates to the phase that we happen to be in as an industry, right? So quantum volume, for example, makes a lot of sense when you're in NISQ level 1, if you want to call it that. I think when you get out to fault tolerant quantum computing, you need to think about things like reliable quantum operations per second, right? So it's really combining how long and how complex of a quantum operation can you run without interruption, getting that essence of reliability and resiliency into a benchmark. So I think the benchmarking work needs to continue and needs to continue with those transitions in mind, right? So it becomes relevant to wherever the state of the industry is. And I think that's a good way to look at it.
Yeah, great. Thank you. Juliet.
Yeah, I definitely agree with Matt that the benchmarking standards are highly dependent on which level of development we're looking at. And to best help the customer, I will say that they really need to identify what they are looking into doing. If someone is really trying to deploy something today on a machine, then sure, they should look at the standard of how to compare NISQ hardware and make sure they are looking into a machine that's a good fit for them. But if they have a more of a long-term approach, then looking at different parameters that allow to compare the FTQC machines is where they need to focus their attention on. So in the end, I think it's best for them to understand what they are looking into achieving in order to compare these quantum computers the right way.
Great, great. Thank you. Miko.
Yeah, so I agree with most of what's said already here. So how the customers see quantum computers today and how they assess them, there's no universal, test suite available. We are not there yet. In the future, I believe we will be there when we are at the fault tolerance stage. But right now, it's really up to the customer. And typically more important than, certain benchmark can be the actual price point. What is their budget? Can you deliver? Then they ask all the reference deliveries, the usability, that do you have this and that framework supported? Yes or no, they have the checkboxes there. This is much more important than, applying some, benchmark or certain hardware spec that is thought to be important because they are very vendor specific. They are very much technology specific today and may not be as usable as a guidance to acquire the best possible product today. But in the future, yes, I think we will have some benchmark coming up when we have logical qubits, and then it can be more or less compared different vendor solutions to each other.
Yeah, got it. Thank you. Michael.
Yeah, from the commercial conversations I've been involved in the last 6 years, if you look at the people who are really pushing global innovation, I'm talking about the early first adopters. They've gone through their organizations, they've talked to the line of business managers, and they've identified various use cases that will drive their business. And what this group is doing now is they have an appetite to run their use cases and workloads on every available device that's out there. So going back to the benchmarking comment, I think there's a real sense in the marketplace that chemistry and material science will run all well on one modality. Optimization, whether it's supply chain optimization or financial optimization, will run better on yet another modality in machine learning. So every use case that comes up, so they will figure out which one of their use cases will run. And I think that'll give them sort of a menu, if you will, to drive towards solutions in the future.
Great. Thanks. Nick, you do
Yeah,
this?
so I just wanted to agree. I just wanted to agree with Michael, absolutely, that like one of the things that we try and enable with CUDA-Q is that it's completely qubit agnostic, so that it can enable exactly that kind of exploration and comparison. So our development platform is made so that you can plug in different backends, so you don't have to choose. And staying agnostic like that, I think, is a great technique for customers as they feel out this kind of emerging field. I also agree with what people have said, that there's not even necessarily going to be a clear winner. It's not clear how that's going to pan out. And the thing I would add about benchmarks specifically, well, I think Echo really, is that when you do move into fault tolerance, benchmarking becomes like a very different challenge and a much trickier one. So then you start to care potentially about things that relate to how applications will actually perform. And to figure that out, you have a lot of work to do, right? So you've got a whole compilation process you have to go through to figure out how that relates specifically to hardware. And moreover, like in that compilation, you can be very clever about how you compile a given application for the kind of constraints and advantages of a particular piece of hardware. So there's an awful lot of thinking you have to do a fair benchmark comparison when you're really thinking about things at the application and fault tolerant application level. So it's I don't think that's a useful answer, but it's just a kind of that you need to be aware of that. We need the tools to be able to make those comparisons, and it's no longer sort of necessarily something that's as simple as a value like quantum volume, as people have already said.
Yeah, thank you. So I'm going to go back to you, Nick, and start this off. So which quantum computing customer segment or segments is pulling investing in the most today? So you guys are all over GPUs and AI, and you've got these efforts in quantum partnering with the hardware vendors. But which customers are pulling? So quantum, a lot of people still think quantum is very hypey. It's still far away. It still needs a lot more investment in engineering, but we're starting to see a lot of progress. But which customers are actually, Miko sort of talked about this a little bit, well, some are spending money, right? What's my ROI? So what are you seeing from your perspective?
Yeah, so this is a great question. So there are a lot of industries that are interested in quantum computing, and it is continuing to grow, the interest. And so I think, you can just basically call out like a number of industries, right? So there's definitely a lot of interest from like chemical industries and from pharma. There's also a lot of interest from automotive. And I think people are coming around to the fact that those kinds of quantum simulation applications, where this is a different meaning for the word quantum simulation, so applications where you're trying to model molecular systems, is looking like, when you go into the fault tolerant era, like earlier generation fault tolerant machines might be more useful. And I think that like the industries are kind of cutting onto that, and so are aware of that. So that's becoming increasingly apparent that those industries are kind of thinking that they might see something in the nearer long term, if you see what I mean. Another interesting area to talk about here is governments. So like there's been a lot of news lately that governments are very much interested in quantum computing, and that they may play like a key role in enabling this technology and taking it to the point where everyone can take advantage of it. And so I think that's also an interesting place to look to see where we might expect the first kind of focus to be in the first useful quantum computers. But yeah, we see a broad range of interest in this, and the key thing for us is to find a way to bring those customers with the right resources to explore their application areas that they're interested in, and also see how like a final quantum computer might look that can kind of address those problems. And of course, to do that, we use all of the tools in our tool set. Yep,
Great, thank you. Miko, what do you think about this? I mean, in terms of your platform, what segment is pulling investing the most today?
Right. If you look at the market really today, and we are on the market today, it really depends on your product and how you position it. And we have a broad product portfolio, what I tried to explain at the beginning. So if you look at the on-premises market, our entry-level product is less than 1 million complete full-stack computer. It's really in demand in places like universities, research institutions, people who couldn't afford a quantum computer really before. If you look at the kind of high end of this on-premise market, the big systems, we have today 50, and in the next year we have this 150 qubit system that goes to places like HPC centers, supercomputers, typically government-backed. If you look at the cloud, our Resonance platform, that's where the interest is coming from the corporate side across the industries. It can be pharma, it can be financial industry, it can be the auto industry for battery research. There's all kind of interest, but from the corporate side for the cloud, it really depends what you're offering today. So cloud goes to the corporate market, and on-prem goes either the universities or the HPC centers. That's how we see the market today.
Yeah, great, thank you. Juliet.
Yeah, so I agree with what was said previously, and right now I think one of the most active customers is partially the government. So we see that within the defense sector, there's been more and more investment in quantum computing, and those are not necessarily things that are obvious to industry players because there's not necessarily like massive announcement for these. but definitely we've had contacts with different governmental agencies that want to know more about our developments, and when we will have these FTQC machines, and when will be a good time to start procurement for these. So I think those remain the first line of customers. And then in the industry side, at Alice and Bob, we tend to focus on the ones that will benefit from an early advantage using our platform, meaning that we are going after the segments that will need a few logical qubits compared to others in order to get an advantage over classical solutions. So those are looking into material simulation or small molecule simulation over large financial use cases that will be like of interest for sure, but that will be very resource intensive, and that will be necessary, like the second generation of fault-tolerant quantum computer. So right now, people that are looking in material simulation could include the automotive sector, when you're thinking about building new catalysts for many use cases in the energy sector, or pharma when they're trying to design very small molecules. So that's our approach right now.
Yeah, great. Thank you. Andre.
Yeah, all good points all around. Government is obviously one of those key sectors that is investing early, and that's a really good thing. From my perspective, I think that although there are like the key industries that we know are vocal today about investing early, like finance, pharma, and so forth, automotive. We have to, put in effort into educating the other industries that are, maybe not investing as much today to make sure that they don't fall behind. We've seen examples of, with the AI boom of certain industries that weren't investing and are now playing catch up.
Yeah.
And I don't think, we want to see those industries, making the same mistake. And that's the argument that we have to make for quantum, and kind of identifying that opportunity, educating them, and being part of their long-term planning strategy, even if it's just identifying who's quantum curious and making those small-term investments initially, and just getting our foot in the door is going to be really important, just to get that process started and kicked off. And that's going to yield benefits down the road.
Great. So Matt, maybe take a shot next. So Microsoft is not a lot of people know this, but you actually have a major effort in quantum, right? So and you're obviously all over classic compute and other aspects. So why? What are you getting from customers at this point?
Yeah, thanks. So I just plus 3 or 4 on the folks that highlighted government as a big important investment space today. That's driving a lot of interest and attention, I think, on technologies that are sort of floating up to the top as being candidates for fault-tolerant quantum computing, which is great. And then to drill in a little bit more on the application side. So several folks mentioned companies that their bread and butter is around chemistry, material science, drug discovery. So we're seeing a lot of interest from customers in those realms that are connecting their desire for application acceleration and how to really rethink how they do their workflows with our Azure Quantum Elements platform, right? So even though there aren't a quantum endpoint available today to provide that dramatically increased level of accuracy for chemical property prediction, the fact that they can onboard today and use the best in the planet high performance compute coupled with AI to rapidly accelerate discovery of new novel compounds and materials to apply to their products, that's really interesting, right? Because they do all that work now, and then they're ready just to redirect to a quantum endpoint when that future is realized. So lots of interest there in that space.
Great. Thanks for that. So Michael, you are the salesperson in this lineup, and so what's going on here? Are you selling stuff?
Absolutely. I think if you go back and historically look at different major trends that have come. So, hit way back and go to like virtualization, the advent of cloud, AI, software-defined data center. What markets or what verticals have jumped in first and why? So, I've heard automotive, finance, oil and gas certainly are big topics or big verticals there. But why is that? And the quick answer is there's a shorter runway towards ROI for those industries. So if they invest heavily up front and become an early first adopter, they'll reap the rewards. If you look at a longer runway industry, such as pharmaceutical, they could do everything right, but they'll know the answer in 15 years, whether they've been successful when they launch a new drug. So those are the verticals I see. Nicholas hit upon something that I'm seeing all the time with government, and it's sovereign AI. Do I want to release my data externally, or do I want to keep it internally, in-house, in my own data center? And you'll see a lot of that in the DoD, the DOE. You'll certainly see governments do that. And it all comes down to data sensitivity. At what level do my internal lawyers go, this isn't leaving the walled fortress. It can't go outside the moat. We have to do this all internally. So you're starting to see that as well. So I see a broader topic of data sensitivity and data management, but also going back to the key industries. So finance, oil and gas are easily the front runners in that area.
So you pierced the veil, so I'm gonna just freestyle this here for a minute. So I wasn't gonna go there, but so there's this whole sovereign quantum computing too, right? So we've got cloud-based. I think Matt and Nick both told me offline in preparation for this that it's convenient, right? But at some point, there's going to be customers, and we heard many of you say government. Governments may say, no, I'm going to have that in my own data center because I want to run algorithms on there that I don't want to show anybody, right? Or something like that, right? And so things have been talked about in prior quantum marketplaces, which is, doing blind quantum computing or, using quantum networking to distributed entanglement so that you could run it on AWS's cloud because it's hosting many quantum computing platforms, et cetera. So how do you see this bright line right now, Michael? I'll just go back to you since you started this. How are you seeing your customers? I mean, versus like government just putting it in their basement versus actually shipping a machine outside your border. How are you seeing that?
What we're seeing in the marketplace is a real appetite to bring this in-house, and simply because of the data sensitivity topic.
Yep.
If you look at various industries, if you look at financial services, will a big bank put their algorithm for derivative trading out on the internet? Well, answer to that is absolutely not. The government's concern when you're looking at top secret data for weapon systems or a DoD contractor, that's all going to need to be in-house in a data center, whether that's a third-party walled off area of a third-party data center or actually on-prem. And this is something that the legal departments of these companies and organizations deal with and wrestle with all the time. What is that threshold when something is too much? Is it too sensitive that we walk it back? And we saw that in virtualization. We saw it in cloud. So I don't think quantum is going to be any different there.
Yeah, great. How are you seeing this, Juliet? Is this coming up for you?
Yeah, no, definitely. And I think the access to quantum computers that we have today will be very different that we will see in the future once we will have FTQC devices. And depending on the sensitivity of data, there might be a will to have on-prem or also private cloud deployment. And we're seeing this from current players that are deploying private clouds for other technologies that quantum computing, that they're getting interest because some of their customers want to get access to this technology but not go through public clouds. So we're seeing this transition happening, but the main point that I want to get here is that how we are accessing quantum computers today will be very different from what we're going to do in the future. And this will be very driven by those organizations with sensitive data, but also with the regulation at the government level. There are some data for some reason that can't leave, for example, Europe. According to your EU regulation. So you'll have to have your machine in Europe if you want to serve the European market, and same with Asia, same with North America. So it's not only at the industrial level, but also at the regulation level that we will see those barriers.
Yep, great, thank you for that. Miko, do you want to comment on this? I think you had mentioned that, and I've seen in the press that you are shipping completed quantum computers to universities and others, as you mentioned, but how much are you seeing this?
Right, so I can actually echo what was also said about this data sensitivity and what Juliet was mentioning about these regulations. So that's part of the story, that why quantum company manufacturers like ourselves, we have to be global. We need to have operations worldwide, because there will be regulation in Europe, in North America, in different countries in Asia. We must have local kind of capabilities to manufacture these computers. The governments have an interest here. We have to be able to be there locally as well. So it's not just on-prem cloud. We need to have both. This is obvious, but also geographically, we have to be present all over the place. And actually, we have to build the capabilities already today. So that's kind of interesting how this will play out. And at least at this moment, it looks like the government interest will be here for the long term.
Yeah. Thank you. Andre, you're also a hardware/software vendor. How do you see this? Is this happening? Are you getting these requests?
Yeah, there's no easy answer to this. Our focus right now is certainly cloud, cloud access, but we're definitely not closing the door on physical delivery. So we see all the pros and cons, and all I would say is that I agree with everything that the others have said so far. There are challenges that come with physical delivery that go beyond all the regulations and data privacy, including the talent that's required to put these systems online and keep them online, especially for customers that don't have that expertise. So that's a huge factor as well. So I would still say we're early, and I think there's still plenty of time to figure it out. Cloud access is a great way to foster the customer base, and we'll be starting there and seeing how it goes.
Yeah, great, thanks. Nick, any comments on this?
I already talked specifically to the customer question again, or
no, it's just we're talking about governments and other customers saying no, I'm good with cloud for now, but I'm gonna put it
on the cloud specifically. Yeah. So I think the cloud is a really important tool to give people access. I think the thing that's going to be, I think that the most impactful, first to wax lyrical, the most impactful early applications on quantum computers are going to be so important, and they're going to be so fundamentally accelerated that people are not going to necessarily, the value of the solution will be so high that the access won't be the biggest problem. So I even think from like that kind of point of view, that it's going to be just people being able to get their data to the machine however they get it there. Whether or not they need it on-prem for security issues, I think is definitely begins to matter when you talk about governments. We've seen a lot of government stuff recently with restrictions on export controls and whatnot. So it's clearly important in that sense. But I think the most important thing is really like to build it, to build the thing, and to people will get their data to it when they need to, I think, because it's going to be that important.
Yep, thank you. Matt, you want to comment, or are you good?
I'll just add that Microsoft, we understand the playbook pretty well for enabling cloud services that meet regulatory requirements and whatnot. So I think that blueprint's pretty well understood. Of course, there'll be situations that sort of demand and require on-prem only. But I think everything up until that, it's something that's fairly well understood, right? So it's as soon as the hardware is ready, it's something that can be deployed at scale in a cloud. Of course, with keeping in mind the challenge of keeping the hardware uptime, right, for this new emergent technology.
Yeah, great. With that, I want to thank everybody